To determine the appropriate conductor size for a 100 kV amps, 80 kW generator operating at 400 volts, 3-phase, we need to calculate the ampacity and then refer to the National Electrical Code, specifically Table 310.15b16. This table provides ampacities of insulated conductors rated 0 to 2000 volts at different temperatures. The generator specifications indicate a continuous current of 144 amps at 40 degrees Celsius. According to NEC section 310.15, the ampacity of conductors must be determined based on the insulation type and temperature rating. Table 310.15b16 lists ampacities for various conductor sizes and temperature ratings. To select the correct conductor size, we need to find the conductor in the table that has an ampacity equal to or greater than the calculated current, 144 amps. Let's look at table 310.15b16. We can see the different conductor sizes and their corresponding ampacities. For example, an 8 American wire gauge conductor has an ampacity of 50 amps, a 6 American wire gauge conductor has an ampacity of 65 amps, a 4 American wire gauge conductor has an ampacity of 85 amps, a 3 American wire gauge conductor has an ampacity of 100 amps, a 2 American wire gauge conductor has an ampacity of 125 amps, a 1 American wire gauge conductor has an ampacity of 150 amps, a 1/0 American wire gauge conductor has an ampacity of 175 amps, a 2/0 American wire gauge conductor has an ampacity of 200 amps, a 3/0 American wire gauge conductor has an ampacity of 225 amps, a 4/0 American wire gauge conductor has an ampacity of 250 amps, a 250 kcmil conductor has an ampacity of 300 amps, a 350 kcmil conductor has an ampacity of 350 amps, a 500 kcmil conductor has an ampacity of 400 amps, a 600 kcmil conductor has an ampacity of 450 amps, a 750 kcmil conductor has an ampacity of 500 amps, and a 1000 kcmil conductor has an ampacity of 600 amps. Based on the table, a 2 American wire gauge conductor has an ampacity of 125 amps, which is less than the required 144 amps. A 1 American wire gauge conductor has an ampacity of 150 amps, which exceeds the required 144 amps. Therefore, a 1 American wire gauge conductor would be suitable based on this initial calculation. However, it's important to note that this is a simplified approach. The NEC requires that we consider several other factors that can affect the ampacity of conductors. Firstly, ambient temperature correction is crucial. Table 310.15b16 provides ampacities at specific ambient temperatures, typically 30 degrees Celsius. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductor must be derated. This means reducing the allowable ampacity to account for the high temperature. The NEC provides correction factors for different temperature ranges. To apply the correction factor, locate the appropriate table in the NEC, which is usually found near table 310.15b16. Find the ambient temperature in the table and identify the corresponding correction factor. Multiply the ampacity from table 310.15b16 by the correction factor to obtain the derated ampacity. Secondly, conductor bundling is another important factor. When multiple current-carrying conductors are bundled together or placed in close proximity, the heat generated by each conductor can raise the overall temperature, reducing the ampacity of each conductor. The NEC provides adjustment factors for the number of current-carrying conductors in a raceway or cable. These adjustment factors are typically found in a table near table 310.15b16. To apply the adjustment factor, count the number of current-carrying conductors in the raceway or cable. Locate the corresponding adjustment factor in the table. Multiply the ampacity from table 310.15b16 by the adjustment factor to obtain the adjusted ampacity. Thirdly, terminal temperature ratings also play a critical role. Electrical equipment, such as circuit breakers and terminals, are designed to operate at specific maximum temperatures. The conductor connected to these terminals must have a temperature rating that is compatible with the terminal temperature rating. The NEC requires that the conductor ampacity be selected based on the lowest temperature rating of the connected terminals or conductors. For example, if a circuit breaker is rated for 75 degrees Celsius, the conductor must be sized based on the 75 degrees Celsius ampacity rating, even if the conductor insulation is rated for 90 degrees Celsius. This ensures that the terminals do not overheat. To determine the appropriate ampacity based on terminal temperature ratings, refer to Table 310.15b16 and select the ampacity that corresponds to the lowest temperature rating of the terminals or conductors. Always use the lowest ampacity value to ensure compliance and safety. Fourthly, voltage drop is an important consideration, especially for long circuit runs. Voltage drop occurs when the voltage at the load end of the circuit is lower than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 5% for power circuits and 3% for lighting circuits. To calculate voltage drop, use the following formula: voltage drop equals current times length times impedance. The impedance of the conductor can be found in the NEC tables. If the calculated voltage drop exceeds the recommended limits, increase the conductor size to reduce the resistance and lower the voltage drop. Larger conductors have lower resistance, which results in less voltage drop. Fifthly, conductor type is important. Different types of conductor insulation have different temperature ratings and ampacities. Common conductor types include THHN, THWN, and XHHW. THHN conductors are typically rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. THWN conductors are rated for 75 degrees Celsius in both wet and dry locations. XHHW conductors are rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. Select the appropriate conductor type based on the environmental conditions and the required temperature rating. Refer to the NEC tables for the ampacities of different conductor types. Sixth, overcurrent protection is vital. The overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the conductor from overload. The NEC specifies that the overcurrent protection device must not exceed the ampacity of the conductor. However, there are some exceptions to this rule, such as when the conductor is part of a motor circuit. To select the appropriate overcurrent protection device, refer to the NEC section 240.4, which provides the rules for overcurrent protection of conductors. Choose a device that is rated to protect the conductor based on its ampacity and the specific application. In the case of the 100 kV amps generator with a continuous current of 144 amps, after considering all these factors, a 1 American wire gauge conductor might still be suitable if the ambient temperature is not too high, the conductors are not bundled, the terminals are rated for at least 75 degrees Celsius, and the voltage drop is within acceptable limits. However, it is always best to consult the NEC and a qualified electrician to ensure that the conductor size is appropriate for the specific installation. The initial selection of a 1 American wire gauge conductor was based solely on the ampacity from Table 310.13b16. A more detailed analysis might reveal that a larger conductor size is required to comply with all applicable NEC requirements. Remember, safety is paramount when working with electricity. Always follow the NEC and consult with a qualified electrician to ensure that the electrical installation is safe and compliant. Ignoring these factors can lead to overheating, insulation damage, and potentially electrical fires. In summary, to determine the correct conductor size for the generator, follow these steps. Firstly, calculate the load current. In this case, it is 144 amps. Secondly, refer to NEC Table 310.15b16 to find the ampacity of different conductor sizes. Thirdly, apply any necessary correction factors for ambient temperature and conductor bundling. Fourthly, consider the terminal temperature ratings of the connected equipment. Fifthly, check for voltage drop and increase the conductor size if necessary. Sixth, select the appropriate conductor type based on the environmental conditions. 7th, choose an overcurrent protection device that decides to protect the conductor. Always consult the NEC and a qualified electrician to ensure compliance and safety. By following these steps, you can select the correct conductor size for the generator and ensure a safe and reliable electrical installation. Always prioritize safety and adhere to the NEC guidelines.